Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on November 29, 2025, about 4 days ago. It introduces NewtonRewards, a physics-grounded post-training method that uses verifiable rewards to make generated videos follow Newtonian motion, delivering an average improvement of about plus 9.75% over the supervised fine-tuned baseline across visual and physics metrics. The paper is titled, "What About Gravity in Video Generation? Post-training Newton's laws with verifiable rewards." And as we will see later, the implications for physics-aware video generation are quite significant. Also, the authors shared an official NewtonRewards repository. Right now it mainly offers a README describing the project and serves as the home for the implementation of their gravity-aware video post-training method. So if you want to inspect or build on their code later, that is where everything will live. Figure 1 makes the main promise concrete. NewtonRewards turns chaotic throws into motion that actually follows gravity. The left diagram sketches a textbook parabolic throw, where an object follows a smooth arc under constant acceleration from gravity. The middle panel, labeled SFT, shows a generated object whose motion bends strangely and breaks that arc. The right panel with NewtonRewards shows the same object tracing a clean, parabolic path that stays consistent with the diagram and with Newtonian dynamics. Figure 2 lays out the 5 motion primitives that NewtonRewards aims to enforce in generated videos. The full figure contrasts simple force diagrams with real-looking example clips, so it connects textbook physics to visual motion. The top row shows freefall, where gravity alone pulls the object straight down. The middle rows cover horizontal and parabolic throws, which combine sideways motion with the same constant downward acceleration. The bottom 2 rows depict a cube sliding down and then up a ramp, where gravity and friction interact along the slope. Figure 3 spells out how NewtonRewards actually trains the video model to respect physics. The left side shows a standard text-conditioned video generator producing a clip of a cube sliding, along with the matching reference simulation. The right side routes both clips through frozen utility models for optical flow and a video encoder, which extract motion and appearance features as measurable proxies. These proxies feed 2 rewards: a kinematic residual that checks constant acceleration, and a mass conservation reward that keeps the object's appearance consistent so gradient updates push the generator toward physically plausible motion. Table 1 defines the 5 natural motion primitives in concrete numerical terms, so it pins down exactly what kinds of gravity-driven motions the model must learn. Each motion primitive is just a basic scenario, like free fall or a ramp slide, that has its own parameter ranges, such as spawn height or launch speed. The left column lists these 5 scenarios, while the right column spells out how they are sampled during simulation, including height bands, speed intervals, ramp angles, and friction settings. Table 2 shows that NewtonRewards is the only post-training method that clearly improves both how videos look and how well they follow Newtonian motion. The table lists visual metrics like L2 and intersection over union, plus physics metrics like root mean squared velocity error, which measures how far motion deviates from the true speed. The NewtonRewards row in the middle achieves the best average gain overall. The 2 ablation rows below reveal why, since removing either the kinematic residual or the mass reward sharply weakens the physics improvements. Table 3 shows that the physics-guided training keeps working even when the test motions differ from training. Out of distribution here means the videos have higher drops, faster throws, and steeper ramps than the model saw before. The top half reports in distribution results, where NewtonRewards cuts errors and slightly improves intersection over union, giving roughly a 10% average gain. The bottom half reports out of distribution results, and NewtonRewards still reduces all 4 error metrics and slightly lifts intersection over union. So the same Newtonian constraints that help match training physics also make the model generalize better to new physical regimes. Alright, the big message is that NewtonRewards shows video models can be nudged toward real physics using verifiable, rule-based rewards instead of human feedback, and this both sharpens motion quality and improves generalization to new scenes. Longer term, this hints at physics-aware generative models as better world simulators. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.